Welcome to AI Podcast. Today we're digging into an EMNLP 2025 survey called Code to Think, Think to Code. Bottom line up front, code and reasoning boost each other in large language models, and the field is finally mapping that loop clearly.
Nice teaser. So the message is basically code makes models think better, and better thinking makes them code better. Did I get that right?
Exactly. The authors, led by Dayu with colleagues from Meta AI, UC San Diego, and the University of Rochester, argue that the relationship is bidirectional and practical. It's not just theory.
Bidirectional how specifically? Give me the elevator pitch.
Think of code as a disciplined workout for the mind of a model. It's structured, executable, and gives instant feedback when you run it. That structure nudges the model to plan, check its steps, and correct itself. Flip it around, and strong reasoning skills let the model do more than autocomplete a function. It can plan tasks, test ideas, and debug across an entire repo.
So code is like a gym with mirrors and a coach. You can see your form and get feedback, and reasoning is the athlete's ability to make a plan and stick to it.
That's a great analogy. The paper even starts with a Mobius strip vibe. Learning to code improves problem solving, and problem solving makes you a better coder. Same with LLMs.
What gap are they filling? Surveys on code models exist. Why this one?
Right. We've had papers on code generation and on reasoning, but not a systematic map of how the two feed each other. Results were scattered across tasks, models, and prompts, making it hard to compare. This survey organizes the space and explains why numbers vary so much across papers.
Okay, so it's a field guide. How do they organize it?
Two halves. First, code-enhanced reasoning. That's where models either train on code or actually write little programs as part of their reasoning. Second, reasoning-enhanced code intelligence. That's where explicit planning, decomposition, and self-reflection improve code generation, code understanding, and ultimately software engineering agents.
Can you unpack the first half? Code-enhanced reasoning. What does that look like in practice?
Picture a math word problem. Instead of juggling everything in text, the model writes a tiny piece of Python to compute an intermediate step, runs it, and uses the output to continue. Frameworks like Program of Thoughts or PAL do exactly that. Others like MathCoder interleave natural language, code, and execution results. The payoff is fewer arithmetic slips and more verifiable steps.
So it's like showing your work, but with code, you can actually execute. If it fails, you get a stack trace instead of a shrug.
Right. And when models are trained with code or code-augmented datasets, they seem to internalize better planning habits. Datasets that add interpreter traces to math problems are a good example. You're basically teaching the model to think like a careful engineer.
Now the other side, reasoning-enhanced code intelligence. How does reasoning make code models better?
The simplest jump is adding chain-of-thought prompts to code generation. That can already lift correctness a bit. Then you move to structured planning before writing code, self-editing after tests fail, and multi-step debugging loops. The best results show up when models treat coding as a process. Plan, draft, run tests, read errors, fix, and repeat.
That sounds like how real developers work. Plan, prototype, test, fix, drink coffee, repeat.
Exactly, and as you scale that up, you get code agents. These systems operate on full repositories, run tools, and try to resolve issues in benchmarks like SWE Bench. Their scores are improving, but they're still far from fully autonomous devs.
Good reality check. I've seen headlines that sound like models are replacing entire teams. On repo-level tasks, they still stumble, right?
They do. Tool fragility, long horizon planning, environment drift. Add in flaky tests and dependency headaches, and the agents hit real-world walls. The survey is careful to show that progress is real, but we shouldn't oversell it.
Do they give any concrete results to help listeners anchor this?
One example on the reasoning side, when the model writes and executes code during math problem solving, top systems have hit the high 90s on a popular grade school math benchmark with very strong base models. It's a striking sign that execution helps. On the code side, using planning and self-debugging, tends to beat plain autocomplete on single-function benchmarks, while repo-level tasks remain much tougher.
Got it. Execution buys reliability on math, structured workflows help code correctness, and agents are promising but fragile. What about how they did the survey? I'm curious how they compared apples to oranges.
They curated recent work from 2021 onward and grouped methods into that two-way taxonomy. Then they summarize reported results on common benchmarks. They also include a plain English section on why numbers vary. Different base models, training data, prompts, temperatures, and even evaluation harnesses.
That's helpful because I often see a single headline number and think, okay, but what base model was that?
Exactly. A method paired with a frontier model can look amazing, while the same method on a smaller model might not. The survey calls that out and urges more contamination-resistant and standardized evaluations.
Speaking of evaluation, what do they say about metrics?
For code generation, pass at K is common. That's basically, did one of the first K attempts pass the unit tests. For reasoning tasks like math, you see exact match. And for agent settings like SWE bench, it's task success rate, as in, did the patch resolve the issue and pass tests? The key point is that single-function tests don't capture maintainability or design quality.
Right. A function that passes a test can still be ugly or brittle. Do they talk about code quality more broadly?
They do. They point to open problems around measuring readability, maintainability, and design aesthetics. In other words, production concerns. Those are hard to quantify, but the paper argues we need to try.
Where do they land on limitations across the field?
A few big ones. First, reproducibility. Many results depend on closed models and custom setups. Second, comparability. Benchmark choices and prompt details swing outcomes. Third, realism. Small, single-file tasks overestimate readiness for real repositories. And fourth, brittleness. Agents break when tools or environments change.
Okay, so what's the author's wish list for researchers from here?
3 buckets. Better evaluation that mirrors real software work, including verified test suites, long horizon tasks, and contamination checks. Better training signals like reinforcement learning with execution feedback, so models learn from running code rather than just predicting text. And richer settings, such as multimodal dev tasks where specs include screenshots or UI diagrams, closer to how front-end and data viz work is really done.
I like the multimodal point. Most specs I've seen in the wild include screenshots, Figma links, or even hand-drawn diagrams. If the model can't use that, it's missing half the brief.
Totally. The survey highlights benchmarks that add images to repo tasks, pushing models to reason across modalities.
Let's ground this for practitioners. If I'm building with LLMs today, what should I take away?
2 pragmatic tips. 1. Let the model write and run small programs as part of its reasoning whenever possible. Think of it like giving the model a calculator and a scratchpad it can execute. 2. Turn code generation into a loop. Plan before code, test during, reflect after. Even simple self-debugging steps can be low-hanging fruit.
And if I'm evaluating tools or papers,
Ask 3 questions. What base model was used? What exact prompts and temperatures? And how realistic is the benchmark? If it's single-file pass at 1 only, it might not predict performance on a messy repo with flaky tests.
Any big picture context they add about where reasoning models are headed?
They note that the new wave of reasoning-centric models raises the ceiling for both sides. As those models mature, we should expect tighter integration of planning, tool use, and verification. But gains will stick only if our evaluations become tougher and more lifelike.
So here's my quick takeaway for listeners. Treat code and reasoning like 2 pedals on a bicycle. Push both and you move forward smoothly. Rely on just one and you wobble.
Perfectly put. Final thought from me. If you want reliable systems, give models executable structure and make them prove their answers. That's the spirit of this survey.
All right, that's a wrap. The paper is Code to Think, Think to Code, presented at EMNLP 2025 by Yang and colleagues from Meta AI, UC San Diego, and the University of Rochester. Worth a read if you're building or evaluating code-capable AI.
Thanks for listening. We'll see you next time on AI Podcast.